So, welcome to the avionics talk by David Madliner. He's going to tell us something about what to do different when building avionics, playing with them, messing around with them. Because there must be a difference between soldering some sensors on a PCB and bringing that thingy to fly or to produce needed data for flying. So, give a warm hand of applause to David Madliner.
Very well. Okay. So, hello everyone. Welcome to my fifth talk. I would like to use the opportunity to dedicate this talk to my little son Vincent, who has today his third birthday. So, feliz cumpleaños. So, we'll start with an introduction on avionics. Then I will talk about some design guidelines that you have to follow if you want to be successful building avionics, and then we will talk about our own avionics, the Red Queen that we will see here in front, and this part. So, what is avionics? This is a very broad term. It's everything that has something to do with electronics that is somehow flying, okay? So what you see here below is the Apollo guidance computer that brought down the lander to the moon, and where there were some problems due to an overflow at this moment. So this is a very complicated device at that time. Today we would put it in a very, very little FPGA. And it consumed a lot of power. I'm not sure how much, but it was in the hundreds of watts. And they needed a lot of energy for that. So let's see. Main functions of avionics. There is the data recorder. Everybody knows that. If something goes down, a plane goes down, everyone is looking for this flight data recorder and the so-called black box, but normally it's red, of course, because black would be very difficult to see. So the recording of flight data is one essential function of any avionics. Then there's housekeeping. It's not very interesting from a certain point of view. It's not about flying, really. It's about looking if everything's going fine. So we will talk about later what housekeeping really is. Then we have telemetry, of course, what Tayo just told us about, and it's sometimes the only way to get any information back from the flight, and so it's a very important feature of any aircraft or spacecraft. So there is, of course, flight control. Some rockets, as this one here, does not need any flight control because ballistically flying, just passively stabilized, but a lot of rockets, especially when they take off very slowly, you have to actively guide them. And of course, in planes, there are a lot of computers helping the pilots to control the flight. So then there's, of course, payload support. Every flying system has some payload of any kind, and the avionics is normally a different system from the payload. So the payload is provided by some agency or university that wants to measure something, or, well, in the military, they want to deploy something, mostly explosive. So the avionics has to give some support to this payload. And then there's, of course, very important and sometimes overseen, the power supply. The power supply is the most important subsystem in an avionics. Why? Because when it fails, nothing works. Very simple. And it's, from a first glance, it is a very simple system, but the devil is in the details. So these are the main functions. Let's talk about flight observables. That would be the aim of the data recorder to obtain. So there is the acceleration. I've talked about inertial navigation. So acceleration and angular velocity is very important. So you can use dead reconing to get the attitude of your aircraft indirectly by integrating, and the position by using the acceleration. Then again, you can use the magnetic field vector if there's nothing disturbing it, and then you can directly measure the attitude of the vehicle towards the magnetic field of the Earth. Then, of course, you could use some more sophisticated sensors like an optical mid-infrared sensor to detect the position of the horizon. That is, you look in a wavelength range between 5 and 15 micron, and then essentially every cloud is transparent and you only see space and Earth. And the temperature difference between these two entities you can then detect with these sensors, and then you can get the attitude of the vehicle in relation to the horizon. Then it's the relative air velocity, as Hayo just said, the frontal probe in front, normally at the tip of the rocket, so it would be inserted here. And this probe would measure the relative velocity of the rocket in relation to the air. So then there's the stagnation temperature that could be also measured at the tip or at the fins. I've talked about that too. So from the stagnation temperature, you can also calculate the relative air velocity. It's another independent observation. And of course, you have to be sure that the stagnation temperature does not get above the temperature that your system was designed for. So if it gets too high, you will have disintegration. So then, of course, ambient pressure, especially when a rocket burns off and falls down to the parachute, and from ambient pressure, you can directly deduce the height of the rocket. And then relative humidity, this is something to correct for any changes in the estimation of the height from the ambient pressure. And there could be, for example, also the local speed of sound is important. Mechanical loads and vibration in the rocket or aircraft. So during flight, especially when the motor is running, there will be a lot of noise and a lot of vibration inside the system. And it could go beyond the design margin, so it could break apart. And it's very important to know why it broke apart and when it broke apart. So if you want to really know what happened, of course you will try to get the debris. But if you could get from the data recorder what really happened, the vibrations in the system and so on, then you can counteract it in your next design. So of course, for example, for a rocket motor, it's very important to see how it's operating. So the burning chamber pressure is relatively easy to obtain, and it shows you how it's working if everything is within the operational margins. If something goes wrong, then you have to abort the mission. So these are some flight observables. There are much, much more, but for our application, these are the main. So let's talk about housekeeping. Housekeeping is not very, I don't know. It's not very refreshing, but it has to be done. So you have to do self-tests. Normally, it's an engineer that takes out the avionics and looks at everything, and that's very difficult because an engineer has only certain amount of time, and it would be nice if the system would yet tell you, everybody of you hopefully knows 2001, yes? If the system just tells you, hey, I've detected a problem, and it will occur in about 12 hours, and you have to replace this part, otherwise we'll have a problem. So self-test is a very interesting function. Then there's subsystem monitoring. As the avionics is normally not one single system, but made up of a lot of subsystems, it is very important to observe the operation of every subsystem. So you could, for example, look at messages distributed over a bus to look if a certain module, for example, stops talking, then you know something is wrong with that module and has to be replaced by another module. So sometimes it's called heartbeat, yes? You may have heard about that. So then it is fault identification. In technical systems, sometimes things can go wrong, and it's very important to sense it before it really gets ugly, okay? So in this case, they didn't. And you have always to anticipate that something will go wrong. You know Murphy, it will go wrong. If anything is possible, it will. So there is the power supply status, very important. Never start a rocket without looking at the fuel gauge of your avionics, that is the battery status or fuel cell status, because there sometimes happens, you have some problems with the engine systems and then you correct it, and then time goes by, some hours later, and then you happily start, and then suddenly you see that your telemetry has stopped transmitting, so you have no data. Then compartment pressure, if you go very high and your compartment is not sealed, then the air will vent and you will have lower pressure, and you can then measure that, and maybe this is something you don't want to happen, because you didn't thorough thermal budget analysis and you want the air to stay inside the compartment. So you should always measure the pressure in your compartment so you can be sure that there is air inside or vacuum, and then you know why it broke. So then, of course, board temperature. If you build avionics, then you should put on every board some little temperature sensor just to look what's happening here. So if something goes wrong, you can look at the temperature, and if it gets higher, then you know, okay, and at this point, something went wrong. And maybe you can make any countermeasures. Then, of course, the payload will consume some energy. Yeah, you have to look at how much it consumes, and if it stays in the defined margins, otherwise you have to cut it off. Sometimes it's very difficult if you are on a satellite, you have a lot of payloads, a lot of subsystems that want energy, and then you have to switch them on in a certain order to avoid the breakdown of the power supply system or maybe overheating of the system. So, and again, especially if you're exposed time for a long time in space, there's always radiation. And radiation has direct effects on the avionics and has accumulative effects on the avionics. So we always talk about the total dosage that avionics can sustain. And this is something that you can measure, for example, with the RUT-FET. This is a specially designed field effect transistor that has a very well-defined insulator at the gate. And then you can measure the charges that are at this gate induced by radiation effects. So this is housekeeping. So it's all about looking after your avionics. If everything is fine, if everything is healthy, if something has to be done to prevent any damage. So there is telemetry. No? Without telemetry, it would be a very boring business, rocketry, because, for example, this rocket here goes up at about 20 G. So you put on the motor, and it just goes off with a roaring sound, and you count to 3, 1, 2, 3, and it's gone. You don't see anything anymore. It's just blue sky or gray sky, and you can't see anymore the rocket. So telemetry is the only way to stay in contact. So you can do on-pad diagnostics. Maybe the igniter is already activated. You don't want to go near this rocket. Maybe it can go off at any moment. So it's good to have telemetry at this moment telling you what is going on in the rocket. Maybe you can also use it to abort the countdown. So then, of course, the real-time flight data. And sometimes you need remote control. So a feedback to the rocket, for example, to change its trajectory. Normally in civil missions, in scientific missions, this is not necessary because you know in advance what you want to do. But in the military, there's often a change of plans, so they have to deviate the trajectory of the vehicle. And of course, sometimes you have to abort. So you have to tell the rocket to disintegrate somehow. So very important, if everything fails, if the main system shut down when it landed and so on, you need a radio beacon so you can have a chance of finding your rocket and your payload. Otherwise, it's almost always lost in the woods. Yeah, it happens. So, what are the functions of an avionics when it controls the flight? There are a lot of things an avionics has to do. First, the launch control. It has to look after the rocket before launch, and it has to. Sometimes it controls the ignition process itself. So it has the possibility with go no go sensors to say no, I cannot launch at this time. We have a problem here, and this is what the people in the NASA in Houston Space Center always monitor. If the avionics tell them that everything is going to be fine just before launch, then when it starts, you have attitude control. So normally very heavy rockets, this one it's not very heavy, but very heavy rockets normally always lift off just vertically. This is because if you would land them a little bit to the side, it just was break in the middle. And they cannot support themselves if you put them under gravity loads. So they really have to start vertically, but they don't want to go upwards. They want maybe to orbitalize, so they have to change during ascent the attitude. And that is what's done, for example, in this case, this is the Ares rocket, just crossing Mach 1. So with the attitude, you can always control the trajectory. Of course, you have to then to modulate your motor too. So attitude alone is not enough. And very important, as I told you, mission abort. So if something goes totally wrong, let's say up there were astronauts, and the solid rocket motor, they are sitting on hundreds of tons of explosive, something goes wrong. And avionics notices this by looking at, for example, pressure sensors in the motor, and they see a spike in the pressure that goes beyond some point, defined point, and know this rocket motor will now explode. And then this avionics is faster than any human could react, and then it will activate the ejection system to bring the astronauts to safety. So recovery, also very important. So if you get down, someone has to eject the parachutes or the aero brake, okay? And the astronauts are not always in a position to do that, maybe because there are high G forces during re-entry, you cannot lift a hand or something like that, or you are just unconscious. And sometimes you don't have any connection to the ground, so there is no team that could help the capsule when it's descending, especially when you are descending on another planet like Mars or in the case of Huygens on Titan. So the avionics has to do everything. It has to know what to do during descent and to recover and land safely. So then there's a payload support. Again, there are so many payloads, so it's very abstract. You need to supply energy to the payload. You have to have some certain protocols to make housekeeping, so that, for example, a scientist that gives you an experiment as payload that is flying a satellite, then he has some special parameters of his instrument that he wants to know. So you have to envision some protocol that this payload gives to the avionics, and the avionics gives it back down over telemetry to the ground, and you can look at your instrument or payload housekeeping. So then, of course, the deployment. Some payloads have to be ejected out of the vehicle, like, for example, CANSATs. So this has to be done by avionics. And, of course, data recording. Yeah, maybe the payload is just a sensor that just produces a stream of data and has in itself no recording facility. So the avionics can lend this to the payload and record the data the payload is producing. And of course, it could be used as a telemetry relay, just pulling out the stream that comes out of the payload down to the ground. So the power supply, as I told you, very important subsystem. If it fails, everything fails. And this is the energy source of everything that goes on in the vehicle. It is normally based on battery packs or fuel cells. This is very, very uncommon, use nuclear engine as a reactors or an RTD. There has to be, and there's always, a redundant power bus. So you don't have only one power line, but several power lines and several subsystems that are connected to it. And very important, especially for battery packs, you need thermal control. Battery packs are made of devices with electrolytes, and this is a liquid containing especially water. And when water freezes, it just destroys the battery pack. It just explodes. So after that, the battery is not usable. So you have to control the temperature in the compartment where the battery pack resides. The same is the case if it gets very hot, then the battery has to be cooled. And that's what happens to a lot of missions on, for example, Mars or so. There is a very long winter night or so, and then the battery pack just freezes over and you lose contact to the vehicle and the avionics. So it's something to the design of avionics, some guidelines. There are some specific requirements that an avionic has to endure. And that is, normally you cannot take with you some bulky stuff. No, it has to be very light, the light as possible. And it shouldn't consume too much power. So the battery packs can be also light, or the fuel cell can be smaller, or the fuel you need can be less. Then sometimes it's necessary, especially in satellites, to give the possibility to make in-flight programming. Especially in scientific experiments, there is a tendency to launch experiments without knowing what they can do. So you launch the satellite into orbit or into a very long path, and from time to time, the satellite comes back to Earth, and then the scientists, in the meantime, as they have nothing to do, they figure out what the experiment does, and they program their own payload, and then when another flyby occurs, they reprogram in flight this payload to achieve what they now can do. So it has to be mechanical robust, because we have a lot of vibrations in a rocket and also in an aircraft and very high accelerations, and maybe in a crash down, for example, for a flight recorder, you want to have something back. So if it just obliterates on crash on Earth, then it's worthless. So it has to be really resilient. And as I said before, it has to be functionally redundant. So as you use several power buses, you will have several devices that have the same equal work to do. So they work in tandem, in parallel, and if some system fails, then maybe the other one can take over. So there's housekeeping and self-test, again, as I said, and very dangerous vacuum operation. So one normally thinks, okay, you take the air away and what? That's nothing important here. But this is really complicated, because if you take away the air, then you take away two ways of transducing heat, by convection and by, what's the other one? Leitung? Conduction, right, thank you. So you take away the possibility to conduct and convect away heat from your electronics. So you have to take this into account. And there's, of course, the necessity due to vacuum operation of thermal management. So if you have electronic bay that gets too hot, you have to cool it down. And the other way, if it gets too cool, you have again to push up the temperature. And very important, if you stay longer in space, you have to do something about radiation. Okay, let's go into the details. So reducing weight, how can you do that? Well, okay, today it's totally normal. You use SMD packages, you use very small chips. That was not normal some years ago. They were using a lot of discrete components. And you use highly integrated chips, especially FPGAs that you can change to the thing you want to do. You can reprogram them without problem. And you have to really think about how to build up your avionics. So you have to optimize how you position the components, not just throwing them on and making a layout. That's okay. It must be really small. So think about what you're doing. And you use miniaturized connectors, so no large connectors allowed. Yeah, they must be small because there are a lot of connectors and they will weigh a lot. And well, this is obvious. Use thin cables. Okay, don't use these large cables because they are too heavy and it can be done. That's too heavy. So then again, you can use very thin board material or even flexible material. It's like if you're building a very lightweight camera, then you will use the same techniques too. Yeah? You will use very thin and light materials to build your electronics. So, and if you do any communication between devices that are at a distance, always use a serial bus, because less wires, less weight, and you can make two serial buses, but it's better than using a parallel bus that is just larger and heavier wire. So, reducing weight. Then, reducing power consumption. Okay, using CMOS is a good idea. So you can have a very low power consumption. There are problems with CMOS, but in the sense of power consumption, it's the best choice. Use low voltage chipsets, okay? So no 5 volt anymore. Go down to 3.3 or 1.8 or something like that. Reduce the clock rate. Most satellite processors run at very low clock rates, like 5 megahertz or something like that, yeah? So they don't get a lot of number crunching done. It is done normally on the ground. They only do the main thing. So avionics is not always a very fast computer. And if you can, use the sleep modes and enable inputs on your circuit. So every time you don't use the subsystem, power it down. And optimize program execution. If you can use tables instead of computing something, use tables, okay? It's very easy to do, but you have to think about it to reduce the total power consumption of your avionics. You can just put your ampere meter there and then try different approaches and routines to do something and look which one will use less power. Power is of the utmost importance. So, in-flight reprogramming, okay, well, what do you have to do? You should be able to make updates and verification during flight, and normally you use multiple solid-state memory devices, so you don't program the memory that is now in use but another, and then you switch to that. And you have to think about some programming protocol that goes over telemetry because you are not able to get with a cable to your device, okay? So, mechanical resilience. Well, it should be a robust enclosure, yeah? Something that is really sturdy, but not too heavy. You can encapsulate your PCBs in resin, normally epoxy or something like that, so they are very, very resilient against vibration and the vacuum. You normally use dampening connectors on your boards. So if there is a strong vibration, and there will be strong vibration, especially in rockets, they don't get directly transmitted to your PCB board, because that can destroy a lot on your board during ascent. Then use shock-absorbing foam. Yeah, you can use aluminum foam, you can use polymer foam, but with polymer foam you have to be sure that it doesn't evaporate too much gas. And then use lock connectors. Don't ever use open connectors. And use nodes. You connect the you really lock the connectors, and then you put a little node around and you seal it. And why? Because in vacuum, everything disintegrates, even the connectors itself, if you stay long enough in space. So sometimes everything that holds together a connection is just a little thing, a node, nothing more. Okay? So, and perform crash tests. So to really believe in your system, you really have to just once test them, let them fall from, okay, not that high, yeah, okay, you don't want to destroy it completely maybe, but let it fall from, let's say, 1 meter or so, and look if it's still working. If something is going wrong, then you know some connector or some problem on the PCB, and you have to look for that. And this is long, long, tedious work. So what about functional redundancy? Well, you can just use multiple identical subsystems. So if you have developed a subsystem, just multiply it and use it in parallel. Normally, you have only problems to synchronize them. And the most simple strategy is just to use two systems, one primary and one alternate system. And the alternate system is normally inactive, but watches the primary system if it is performing in the parameters defined. So you have to find the parameters that define a correct operation. That's called the heartbeat. So the alternate system watches the primary system, and if the primary system goes offline, then the alternate system powers up and takes over. This is the simplest possible redundant solution. And what is often used is triple modular redundancy, or even more, with 5 systems or so, where 3 systems run synchronously, performing the same actions with the same inputs, and then there is a voting logic behind them, and the majority wins. So if one system fails to compute correctly, the other 2 can overvote it, and there would be no harm done. And of course, you can improve the number of systems that are competing. There's only one backdraw, and it's when the voting logic fails, everything fails too. But this voting logic is normally made of very resilient devices. So, and one important thing, use different approaches. So if you have, for example, an avionic performing some task like attitude control, make 2. So envision 2 teams building the same thing, but on totally different devices with totally different programming languages doing exactly the same thing. Then they won't fail at the same moment, normally. So some guidelines to housekeeping and self-testing. Always observe what is going on electrically in your system. So put shunts on your boards, look at the currents that go through, look at the voltages at certain test points, and look at the temperatures. Always look at these 3 things. Otherwise, there will be consequences. Always use circuits that notice when the power is going down, so you can countermeasure it somehow, maybe. Use watchdog timers, and monitor the radiation background. And so this is done, for example, you can use photodiodes to use to measure the gamma ray background. Very simple, very cheap, it's not very difficult, and so you could, for example, if you're going in a satellite through the Van Allen belt or the South Atlantic anomaly, then you see that the radiation goes up. Then you shut down all systems, okay, and you wait until it goes down the radiation background, and you go up again. So vacuum operation. There is a problem with certain metals. If you put them in vacuum, they just evaporate, they sublimate, and then they resublimate on any surface available. So especially cadmium. Luckily, we have ROHS today, but some years ago, this was a real problem. And for example, at ESA, before you come as a payload specialist to insert anything in their computers, in their avionics, they explicitly check the connectors if this is any cadmium on it, and they give you special certified connectors that are absolutely cadmium-free as an interface, okay? Because they are really, really aware of the problem that any amount, and be it just a milligram of cadmium in the system, could ruin avionics in vacuum. There are other methods too that do that. Always avoid polymers containing plastifiers, like PVC, for example, soft PVC. These plastifiers in vacuum will just evaporate and condensate on everything. So if you have a camera, maybe after a few hours of operation, this camera will just go dark due to the plastifiers recondensing on the optical system. Avoid fluoropolymers, especially Teflon. That's nothing for space. It just gets it just disintegrates over time. It's very radiation, it does not tolerate much of radiation. Use reactive adhesive that really bond strongly together, nothing with plastifiers or so. Use, for example, epoxy or polyurethane, something that really reacts chemically. So nothing is left to evaporate. Use tapes based on polyimide, very, very good material. It is very sturdy. Radiation does nothing to it, well, a little bit, but it repairs itself. So Kapton is one of the best tapes there is in the world, and every other polyimide-based tape too. And again, testing. Build a vacuum chamber and check if your electronics will outgas in vacuum, and if your electronic will survive the thermal management will work. So if it will heat up or something, or cool down too much, that can be tested in a vacuum chamber. So about thermal management, you have to model your thermal budget of a system, especially if you're building a satellite. There's no way around. If you build a rocket that will only stay for a few minutes in space, there's a problem. You just put it on a seal, there's air inside it, there will be convection and conduction, no problem. But if you stay in space in a vacuum, you really have to model the outline of the whole system, look where are the heat sources, and then model how the heat will flow through the system, what temperatures will be in each device. So a good idea is to use always ground planes on your boards and heat pipes to distribute the heat. So you can just take a copper wire and solder it to one point and then lead it to another point just to transport the heat, because this will transport effectively heat as air did before. So use temperature control, as I said, put on everything that is somehow sensitive to temperature variations, put a sensor on it. I cannot say this enough, because there were a lot of failures due to not looking at what is happening to avionics in space, in vacuum. Adjust the emissivity of surface to adjust thermal budget. So if you have a problem, if something gets really, really hot, then just make it black. Okay, just paint it in black or put something black on it, so it will effectively radiate effectively. Yeah, and to accept this radiation on other surfaces that are cold, you have to make them black too. Okay, so if everything is silvery and shiny, it's very bad for thermal budget. Okay, so use dark components. And of course, test the operation vacuum chamber with a sun simulator. So put a 1 kilowatt lamp and shine on your electronics in vacuum, and you will see that something will happen to this board. It will heat up enormously. So radiation hardening, this is very, very difficult. This is very difficult because you have to do compromises, and normally you don't have the money to buy the really expensive stuff. There are chips that are based on so-called insulating substances. This is silicon on sapphire, or silicon on insulated. It is silicon dioxide. And these chips are more resilient against radiation, because when an ionized particle goes through the chip, it produces a cascade of ion-electron pairs. And if they go through an insulator, this cascade of ions and electrons stays in the insulator, it cannot move. So it cannot flood the circuit that is built above the insulator. If it's made also of silicon substrate, the chip, then from the silicon semiconductor, these pairs will just swamp over to the circuit and maybe damage its operation. So bipolar devices are very good for very high dosages. So for very high dosages, CMOS is normally not a good choice. except if you can make thermal cycles. So it's very interesting. The problem with CMOS devices is that the insulators between the gate and the channel that control the flow, this insulator gets charged over time by the radioactive bombardment. And if you heat it up, so you have some kind of a Schottky effect. Yeah? If you heat it up, this effect can heal again. But you have to heal it up to 150, 250 degrees Celsius. So this is not done in normal operation. You have to design it in, okay? So, of course, additional shielding helps. So putting something, an aluminum part of, let's say, 5 millimeters over it or something will help. The problem is, if you are in outer space where the cosmic background radiation comes, so the really high energetic particles with 1 tera electron volt or something like that, then additional shielding can be bad, because the additional matter in front of your electronic devices is the material where these very high energetic particles can produce neutrons and so on. And so actually, if you overdo it with the shielding, not only your avionics will get very heavy, but you will worsen the situation for radiation. So you have to calculate it, okay? There are simulation programs for that. Normally replace DRAM with SRAM. It's just more stable against single effect upsets. Use always error correcting memory. There are always bit flips all the time, so if it's only a single bit flip, this can correct it. Use substrates with wide band gap. That's very similar to the thing with the insulating substrates. If you have a very wide band gap, the ionizing particle cannot produce so much electron-ion pairs. Use depleted boron to shield against neutrons, especially in nuclear reactors, but also if you are in space, there will be a production of neutrons. And boron 11 has a very high efficiency to capture neutrons, so to protect your electronics against neutrons, because neutrons are the worst radiation effects possible, because they go into your semiconductor, then interact with a nucleus and make it radioactive. So when it blows up, it leaves a defect, and this changes, of course, the semiconductor's properties. And this is something you don't want to. So neutrons are very dangerous. And of course, you can test the operation of avionics by putting it into an accelerator. Now, for example, we have the possibility to go to the GSI near Frankfurt and put our stuff in a particle accelerator to test if it's working at a certain amount of kiloreds. So let's talk now about the avionics we have built. So this is mainly the lower part. So this is this part here. So we have here the DPU 0, and then an analog digital converter, ADC 0, and then we have here the INA, the inertial navigation subsystem. So on this DPU is data processing unit, there is an SD card that just records everything that happens, that is measured by the ADC, and that is by the inertial navigation. So the data flows through the ADC to the DPU onto the SD. So if you recover the SD, you have all the flight data you want. The problem is sometimes you don't find it in the rocket. So we made the following compromise. We built into the tip of the rocket, this is the tip, the nose, another subsystem. So, where are you? So, well, these two boards here, this is the DPU, and this is the second analog device converter. These receive a stream of data from the lower section. So all the data that comes from here is transferred to the upper DPU. It also puts it on an SD card, just to be sure. And then it sends it over telemetry. So on the upper unit has 2 additional tasks to perform. First, it has a second analog device converter, and it measures the relative velocity with a Prandtl probe, the temperature at the stagnation point, the stagnation temperature, and the ambient pressure. Yeah, these three observables. And we have a GPS receiver on board, a GPS mouse. So if the deployment works, we will have GPS information on the location of our rocket. So this is a principal overview of the system. Now I want to talk about the function. Well, it has housekeeping, a data recorder, as I told you, telemetry, and of course you need a power supply. So for example, for the power supply, we designed a special compartment to use normal battery cells. The problem is that normal battery cells, you can put them in these I don't know, cradles made out of some polymers with some thingies that hold them together. They are not very reliable. We use them too, and especially at high acceleration and vibrations, something goes wrong. Yeah? Or maybe it's just a little bit of humidity and you have corrosion, and then at the moment of liftoff, something just moves and then you have no contact and no power. Okay? So to avoid this, we designed a special compartment it's like a revolver. So 6 batteries in one compartment, and it works fine. Well, we'll see when it flies. It has never flown till this date. So this is the power supply. Well, this is the schematic of the data processing unit. It's very simple indeed. Today, there's no much components you have to put on a board. So this here is the so-called propeller. We'll talk about it in a second. It's a chip from Parallax. I don't know. Who knows the propeller? Ah, very good. So, okay. So we know what I'm talking about. So the propeller is very versatile. You just put on some connectors, and then later on you see what you do with it. And this is just a power supply, the regulators for 3.3 and 5 volts. And up there's the EEPROM, and the rest are just connectors. Connectors. So this is the board, it's 60 times 60. So we have only one chip in the middle, a propeller here, and then 2 normal 10-pin connectors. And here is something for an SD card. This is the SD card. And on this version, there are these modular, Western modular jackets where they are too big, and we'll change it in the next version. So up there goes in the power. We have some HF output for video, if necessary. So this is the schematic of the propeller for all of you that don't know this great chip. It's, in a sense, a redundant system. That's why I was very interested in using it. It consists of 8 absolutely identical units called the cogs. And they are connected to a so-called hub. So you have cog 0, 1, 2, 3, and so on. And you have one memory of 32K, it's SRAM. So every cog has just a small time to communicate with this SRAM, with the main memory, over the hub, and then it switches again. So this hub is always rotating, only connecting one cog to the other. But it's transparent to the programmer. You don't see it. You only see that the commands that are trying to exchange data with the hub memory will be longer in duration. So every cog consists of 2 counters, 2 32-bit counters that can be used to produce PLL. You can make DUX from it or an ADC, or just count things. And then you have a video generator on every cog. So this is very funny. If you want to make video games or some blinking devices, it's very, very easy to use. So on every of these cogs has access to 32 pins. So we have exactly 32 I/O pins, and every cog can access them. So you just build your device. You don't think about what you will do. You don't think about what we will do. We will just build it, and when you're ready, then you can think about, okay, what will I do today? And then you can define every pin to a new function. Yes, you can put on every cog a new I/O controller. For example, an SPI controller, or an asynchronous, an UART, or whatever you want. So every cog will have an independent program that will run concurrently. In total, at 80 megahertz of clock rate, you will have about 160 million instructions per second from this device. And you can clock it up to get about 200 MIPS. So it's fast. And it's very simple to program. And I'm very happy that it's very cheap. So you can get it for about €7 at the moment. Okay, let's look at the ADC. The module is based on 2 analog digital converters that each has 6 channels. So every module has 12 channels for any sensor. And it's also very simple. So we have here something for the reference voltage, and you have the voltage regulators for 3.3 and 5.0 volt. And these are the 2 ADCs, and these are a lot of connectors. So again, very simple. This is a board, same format, 60 times 60 millimeters. And the connectors dominate the board. So you have here a row of connectors, 6 and 6, so you have 12 connectors to measure differential voltages. So especially for whetstone bridges, for pressure gauges and so on. Every transducer without any electronics in front of it can be measured with this ADC unit. So, and they're very small, so in reality they are just a few millimeters wide and can be found in the backplane. So, just a word about the ADC itself. It's made by Analog Devices, and it's very easy to use because it has an SPI interface. You just have to give him a reference voltage, nothing else, and connect here to the analog inputs your voltages. That's all. And then the rest is software. And you can go as is 24-bit, so you can go down below, it depends of course of the noise of the system, but it has a precision of below microvolt. So this is what we use. And this is for the telemetry. This is a very simple schematic because we use a module made by Hope RF, a Chinese company. And this is also controlled by SPI. So you just communicate digital with it, and this module does everything. So you just give in a digital data stream, and the telemetry puts out the HF, and on the other side it receives it and puts out your digital data stream again. Very simple. And this is the board. Not very complicated. So, now I want to talk in the last minutes about the software design of this avionic at the moment. Everything is made of objects in the propeller. So every cog is one object. So normally you have sensors producing a stream of information. It may be, in this case, the ADC that is measuring some voltages, or the GPS, or any other sensor you can think of. And what you have to do is you make a ring buffer, and in this ring buffer you put your stream of data, okay? And this object, I call it the streamer, it just collects the data from the string buffer and puts it again in a linear buffer. And when one linear buffer is full, it's exactly 512 bytes, it writes it to an SD card. So we don't use any FAT or something like that. We just write it plain down to the SD card because we want to have as much information as possible. So we want to be as fast as possible. And after this happens, the streamer parses the linear buffers and looks for so-called sentences. We use the same format like the GPS, the NME sentences. So it starts with $1 and ends with a carriage return line feed. And then he puts it into the demuxer, and from there it goes to telemetry out. So in reality, the main problem, this looks very easy. The main problem is that the sensors have different rates of producing data. Yeah? So the GPS will send you data at about 4,800 baud, but only once a second, a short GPS message. The ADC may be producing 50, 100 kilobytes per second. Okay? And so if you would just stream it to the telemetry, you would never get any GPS information down. So the streamer has to make a prioritization and say, okay, you have talked enough, now you have to get some sentence through. Otherwise, you wouldn't know where the rocket is, okay? Because the ADC would just flood the system, okay? So this was something to the software, and I think I'm done now. Okay, thank you.
Thanks, David. If you have any questions, please line up behind the microphone and talk on that microphone next to Krish at the sound desk.
Yes.
That close. Oh, that close. Okay. That you use the processor as the main processor. Do you also use the different cogs for redundancy in your software design, actually?
At the moment, we use on every subsystem the same code. That's true. We have a second group that wanted to build another version with different code, yes, but at the moment it's only one code version.
More questions?
How tight is your energy budget? I saw on the schematics linear voltage regulators, and they are known not to be very efficient.
Yeah, but they're not very efficient, but they don't produce noise. Noise is the most important thing. Of course, we could use other regulators, but if you use buck boost or something like that, you would introduce a plethora of noise at 100 kilohertz and more. It depends on the switching frequency. So these kinds of regulators are not, you cannot use them in avionics. It would just flood the whole system with dirt, with noise. Let's say one propeller at full speed uses about 100 milliamps at 3.3, so 0.33 watt per processor. And the ADCs, they are not to mention, it's very, very low power consumption because they are slow too. And the SD card uses a little bit. So in total, I think the whole avionics uses about less than 1 ampere, less than 3 watt. Okay, the most power consuming subunit are the telemetry, especially the radio beacon here. This consumes a lot of power. How much is it? So at 12 volts, something like a little more than 1 watt. Yeah. It's very powerful for its size. But in total, we can run this avionic hours on a fresh battery pack. Yeah, so 12 hours or so or more. Yeah.
Hello, do you see any option to get full redundancy to remove this voting machine, I think you called it,
The problem is that if, for example, attitude control, which is very, very important for rockets and other UAVs too. If you have some attitude control subsystem that is made of some engines, some cold gas engines, then they are, let's say, 3 computers, they are performing the same algorithm, and one of them wants to do something else than the other 2. Then they will overvote them. But if you have really, in a sense, totally redundant, so 2 subsystems that could control the attitude, then if one subsystem goes wrong, the other has to correct for it.
Yeah.
Yeah, this is very difficult, because if the one thruster just, let's say, just opens one valve totally, the other cannot overpower it. And so you're in a stalemate, okay? Yeah. And you lose control. So this is a really difficult problem. There's no exact solution to it at the moment. Although I don't know of any. Yeah, it's always a problem if you have very delicate subsystems like the attitude control system. Something goes wrong, you're just screwed. It's a point. So you really are very, very dedicated to be sure that this system is thoroughly tested, that it doesn't malfunction at the moment where you need it.
Yeah, because when the voting machine fails, it could be a problem, because I think it's not, you said it's very simple, but I imagine it's a little bit hard because you have frames, because the sensors act different. It's not totally determined what the output. So you don't have 2 same outputs and one failing. We have the same problem with the quads. You have to get it really stable, and to get 3 subsystems with no total redundancy would be great. Yeah.
Yeah, there are problems where you can do that. There are problems, for example, in power supply. If one power supply, when one power source goes down, the other 2 work, no problem. The problem is if you have time-critical application, and if one system says something contradicting to the other, then they are at a stalemate. Okay, you cannot say that one system can be stronger than the other, because they are all equally, they are all equal. So that's a real problem. I don't know how to solve it at the moment. Maybe there's a solution. Yeah?
Thank you.
Is the software programmed in Spin or in assembler?
Both. So the software you saw just one before, this is all programmed in assembler. It has to be very fast. Especially the routines that write down to the SD card, this could not be done in Spin. It's just too slow. And everything is programmed in assembler, but of course the main program has to initiate initialize the objects is done in Spin. Yes, but everything is done in assembler.
Did you use some objects from Parallax Object Exchange?
Let me think. Yes, I took these one object that uses the SD card. I forgot it. It's the most used one. Very good. And I just took the assembler routines that wrote directly to the SD card and omitted all the fat stuff and so on. Yes, that was used. But the rest, no. It's everything is. It's so special. I've never seen such a system. Otherwise, I've used it. The problem is that you have data streams with so different data rates, and you don't know what will be the next system configuration, and you don't want to rewrite everything every time. You just want a system where you just put, well, an object with a ring buffer, and then you just read it out. It does not depend on the data rate. It could be 1 byte per second or 100 kilobyte per second. It doesn't matter. It will work. That's the point. Okay. So everything is done as assembler, yes.
The board design and the software will be available?
You can have it from us, yes. Sure. It's
Okay.
very easy, anyway.
Any more questions?
A question from IRC. Why don't you use u-blox GPS modules, which obviously have only 5 Hz output rate?
Actually, we use two different, and one is the Venus GPS that has 10 Hz output rate, I think. Yes. No, u-blox is very good. It's very good. It doesn't matter really which you choose, because today there are so many good GPS modules. But u-blox I know is very good, and the problem was just which module was at hand. So we had the Venus GPS module, and we used this at the moment. Okay. But feel free to donate anything to us. We take every GPS module available.
So when there are no more questions, and I would like you to stand up now, if you have any questions, then please take all your waste, luggage, stuff, empty bottles outside of the shelter, and directly after the shelter there is a place to dispose of that. Thanks.